Okay, how does that make sense? Now, let's do two questions from some recent papers, which are very important. You will see a couple of other questions like this in recent papers as well. And it's an important concept that they did not use to test before, but in the last 2-3 years, similar questions have come up multiple times. So let's have a look at this. This is from June 2022, paper 4, variant 3, question number 4 from that. Let's have a look at this. It says the diagram shows a block of mass 10 kilograms that's suspended below a horizontal ceiling by two strings AC and BC of lengths 0.8 meters and 0.6 meters. Attached to fixed points on the ceiling, you can see that here, there are two strings. One has length 0.8 meters and the other has length 0.6 meters. The angle ACB is 90 degrees. There's a horizontal force of magnitude F Newton that's acting here on the block, and the block is in equilibrium. Now, everything else is mentioned on that diagram. The only thing that's not mentioned is that the block is in equilibrium. So you can highlight that, so keep that in mind. And now in the first part, it says, in the case where F equals 20, find the tensions in each of the strings. So in the first part, they've told you what the value of F is. And that they're saying is 20 Newton. Now, this part is relatively straightforward. There's not much complication here. Let's try this first, then look at the second part after that. So it's equilibrium. That means the opposite forces are going to be equal to each other. So all we have to do is just resolve the forces. First of all, represent all the forces acting on the block, and then equate the opposite forces. Forces acting towards the left side equal the forces acting towards the right side, and upward forces equal the downward forces. But for that, we need to represent all the forces first. The mass is 10 kilograms. What about the weight of the block? It's going to be 100 Newton acting in the downward direction. That's the weight of the object, weight of the block. Then you have this force acting towards the right side. That's already mentioned there, 20 Newton. That's the force F, 20 Newton. Instead of F, you can write 20 there. What else? You have two strings attached here, one here and the other here. There's going to be tension in those strings. In which direction do the tensions apply? Away from the block. So one tension is going to be in this direction. Let's call that T1. And the other tension is going to be in this direction. Let's call that T2. These are all the forces acting on this block. Now, we first need to resolve these forces. How do we resolve these forces? 20 is already horizontal, 100 is already vertical. These forces that are acting at angles, these are the forces that need to be resolved. Okay. Now, for resolving forces, we need angles. We don't have any angles given. However, they have given us the lengths of these strings. And the whole point of giving lengths in such questions is that they allow you to find the angles that you're looking for. It's a right angle triangle, and you know two sides of that right angle triangle. One is 0.8 and the other is 0.6. You can use that right angle triangle to find these angles. Now you can find this angle and this angle. Let's start with any one of them. Let's call this angle theta1. How can you find theta1? This is 0.8, this is 0.6. 0.8 is adjacent to that angle. 0.6 is opposite of that angle. What ratio do we have between perpendicular and base? Opposite and adjacent, we have tan. So we can say tan of theta1, that equals opposite, which is 0.6, divided by 0.8. And from that, we can find the value of theta1. Can somebody tell me what this value is? Theta1.
Uh, 36.87.
36.87. Okay, so that's the first value, 36.87. Now, if this is 36.87, then what about the other one? It's a right angle triangle. The other one is going to be 90 minus 36.87. That will turn out to be 53.13. Okay, so we now we know both of those angles. Okay, this is for 53.13, and the other one that we've just found, this angle is 36.87. Now, that was the whole point of giving those lengths. There's no other use of the lengths that we were given there. Okay, that was the only use of these lengths. We have found the angles. What do we do now? We can just resolve these forces now. T1 and T2, I'm going to get rid of those lengths from there because they're no longer needed. This is T1 and this is T2. Okay, let's resolve T1 first. There are going to be two components of T1, one acting in this direction and one acting vertically upwards. If this angle is 36.87, we can say this is an alternate angle to that. This is also going to be 36.87. So there are going to be two components of T1, one acting towards the left side. That one is going to be T1 cos 36.87 because that's adjacent to the angle. And the one acting vertically upwards, that is going to be T1 sine 36.87. These are the two components of T1. Then what about T2? We have one component acting towards the right side and one component acting vertically upwards. Now, if this angle is 53.13, that means this is also 53.13. Again, alternate angles. The component adjacent to the angle, that is going to have cos. So we have T2 cos 53.13. And on this side, we have T2 sine 53.13. And that's it. These are all the forces resolved. Now we just have to equate the opposite forces. By the way, just a quick check with you. Do you think we can use Lamy's theorem here, by the way? Will that work?
No, sir, because there is an external force of 20 Newton on the right side.
And that makes the total number of forces 4.
4.
Yeah, so we need 3 forces to be able to use Lamy's theorem. These are 4 forces, so we can't use that. Otherwise, that would have been much quicker. But in this case, we can't because we have 20 Newton here, 100 Newton here, and then T1 and T2. That's 4 forces. Lamy's theorem requires 3 forces, so we can't use that. So that's the only way we are going to have to do it by resolving forces then. Let's equate the opposite forces. We have some horizontal forces. We have T1 cos 36.87 acting towards the left. And towards the right, we have these 2 forces. Upwards forces are T1 sine 36.87 and T2 sine 53.13, and downward forces 100. Just equate the opposite forces because it's equilibrium. So we say the forces acting towards the left side, they should be equal to the forces acting towards the right side. The upward forces, they should equal the downward forces. Okay. So what do we get now? T1 cos 36.87, that's the force acting towards the left side. Towards the right, we have 20 plus T2 cos 53.13. That's one equation. And then upwards forces T1 sine 36.87, T1 sine 36.87 plus T2 sine 53.13. That equals the downward force, which is 100. These are 2 equations. We are just going to solve them simultaneously, and that's going to give us the values of T1 and T2. So it says find the tensions in each of the strings. So we have to find both tensions, T1 and T2. We can just solve these equations and find those 2 tensions. Let's evaluate this now. Cos of 36.87, that's giving me 0.799999. If we were to round it off, in fact, if we were to use the exact value of this angle, you're going to get 0.8 from that, 0.8 T1. On the other side, you have 20 plus T2 into cos of 53.13. That's giving me 0.6, almost exact. So that's 0.6 T2. That's one equation. Okay, let's look at the second one. Sine 36.87, that's 0.6. So that's 0.6 T1 plus sine 53.13, that is 0.8. So we have 0.8 T2 equal to 100. These are 2 equations. Just solve them simultaneously and you will get the values of T1 and T2. How do we solve them simultaneously? We can make any one variable the subject in one equation. Let's say we use the first one to make T1 the subject. T1 equals, so I'm dividing the whole equation by 0.8. Okay, 20 over 0.8, what's that? 25. So 25 plus 0.6 divided by 0.8, that's giving me 0.75, 0.75 T2. That's my first equation. I've made T1 the subject here. So I've just divided the whole equation by 0.8. Okay, so that gets me T1 on the left side, on the right side I get 25 plus 0.75 T2. Let's put this in the other equation now. When we put this in the other equation, we get 0.6 into 25 plus 0.75 T2 plus 0.8 T2, that equals 100. And now let's simplify this. 25 into 0.6, that's going to be 15, plus 0.6 into 0.75, that's 0.45 T2 plus 0.8 T2 equals 100. Now 0.45 plus 0.8, that's 1.25. T2 equals 100 minus 15, that's 85. And then T2 equals 85 over 1.25. Let's see what that is. That is giving me 68 Newton. T2 turns out to be 68 Newton. Okay, so that's tension in the second string. Let's put that in the first equation now. What does that give us? T1 equals 25 plus 0.75 into T2, which is 68. And what's that now? 25 plus 0.75 into 68, that's giving me 676 Newton. That's the other tension that we were looking for. So now we have the values of T1 and T2. Make sense?
Yes,
Any
sir.
problem with this? Any questions, anyone? No?
No, sir.
All right, so that was the first part, pretty straightforward. We just input that value of F there, 20, and equate the opposite forces. Let's look at the second part now. That is the reason why I chose this question. Part B. Now it says find the greatest value of F for which the block remains in equilibrium in the position shown. Now, what does that mean? Let's think about this. I'm just going to copy this diagram. Before that, this. Okay, so this is what we have in the first part. We have all the forces represented here already. When you're doing this in an exam, as I've said before as well, you should be doing this annotation using a pencil so that you can just change that or modify that for the next part. Now I can copy that, so I'll just copy that here like this. Now in the second part, it says find the greatest value of F. Now the first thing you should realize is this value of F 20 Newton, that was only valid for the first part. It's not valid anymore for the second part. That was only for the first part. Okay, so you can't use 20 here anymore. This is not 20. This is just F now. Okay, we need to find the greatest possible value of this force F such that the block will remain in equilibrium in this position. Now let's think about this for a moment. What does it mean? The block will remain in equilibrium in this position. You have this force F acting towards the right side, this force. Now, if I were to increase this force by a lot, let's say if I were to make it 1000 Newton towards the right side. Now that's a very big force compared to the weight that we have here. What's going to happen is the block is going to move towards the right side like this. So if this force F was too big, eventually this equilibrium position is going to change and the block will move to the right side. Okay, like this. What we need to do is we need to find the greatest possible value of f such that the block will remain in this position and it will not move towards the right. So if f was, for instance, just 1 Newton, then you can expect the block not to move, right? It will stay in its position. So between 1 Newton and 1000 Newton, there is some point, where this equilibrium position is going to change. What is that point? That is what we're looking for. So we're looking for the greatest possible value of f such that this equilibrium position will not change. Okay, so that's the question. Now, everything here is exactly the same as in the previous part. Nothing has changed except the value of f. In the first part, we were given that the value of f is 20. Now we don't have that value, but it's still equilibrium like before. So the opposite forces are still going to be equal. The forces acting towards the left side are still going to be equal to the forces acting towards the right side. Upwards forces are still going to be equal to the downward forces. So these equations that we wrote here, they are still valid. These equations, these are still valid. Okay, so I'm just going to copy them here because they're still valid. The left forces acting towards the left, they are still equal to the forces acting towards the right. The forces acting upwards are still equal to the forces acting downwards. Instead of 20, we have f now. What we are looking for is the greatest possible value of f. Okay. Now, how do we think about this? How do you find this greatest value? There are two ways of thinking about this. We'll discuss both of them. One possibility is that you think of these equations. So think of it just in mathematical terms. So forget about the diagram for a moment. Just think of it in mathematical terms that we have these two equations. How can we maximize the value of f such that these equations will still hold true? What would be the maximum value of f such that these equations will remain correct, remain true? Okay. All right. Now, how do we do that? First of all, we can make f the subject. Okay, because we're trying to understand f, we need to find the greatest possible value of f. For that, we first make f the subject. To understand what f is equal to, f is going to be equal to 0.81 minus 0.62. Right, that's what the value of f is. 0.81 minus 0.62. We want to maximize f. What is f equal to? F is equal to 0.81 minus 0.62. That is what f is equal to. How can we maximize the value of f? If we want to maximize f, T1 needs to be as big as possible because that's the positive value here. And this thing is being subtracted. If we want to maximize f, T2 needs to be as small as possible, right? T1 needs to be as big as possible, and sorry, T1 needs to be as big as possible, and T2 needs to be as small as possible. Now, how do we maximize T1? Can we give it some large value? But what large value? There's also a limit to T1, and that is that the sum of 0.6 T1 and 0.8 T2, that has to equal 100. So if, for instance, you were to put T1 equal to 1000, if it was a very large value, then this equation cannot hold true because then you would have 600 plus 0.8 T2 equals 100. Now, this will not hold true because you already have 600 here. It's bigger than 100. So how big can we make T1? It's not easy to figure out. Okay? It's not easy to figure out how big T1 can be. What we can think about is how small T2 can be. We want T2 to be as small as possible. Now, what's the least value we could put to a force? It can't be negative, right? the least value of T2 that we can have is that we can make it 0, right? We can make T2 equal to 0. That would maximize F. So that's what we do. We say to maximize the value of F, T2 should be equal to 0. We want to maximize T1, minimize T2. We can't figure out what the maximum value of T1 could be, right? That's not straightforward, but we can figure out what the least value of T2 can be, and that is 0 Newton. Okay, so what we do now is we put T2 equal to 0. Okay, so we put T2 equal to 0. That's what we do. Now, when we do that, what do we get in the first equation? We get F equal to 0.8 T1 minus 0.6 into 0. Now, we still have two unknowns here. We put T2 equal to 0 in the second equation as well. That gives us 0.6 T1 plus 0.8 into 0. That equals 100. And that gives us 0.6 T1 equal to 100. T1 turns out to be 100 over 0.6, which is 166.67 Newton. That's the maximum possible value of T1 that we have. Then we can input this back in this first equation. Instead of T1, what that gives us is 0.8 into 166.67 minus 0. That turns out to be 133.33 Newton. That's the maximum possible value of F that we can have here. It can't be bigger than this. This is the maximum possible value of F. That is one way to think about this. Using these equations, since you're looking for the greatest possible value of F, you're saying, let's make that the subject. And now we just need to maximize T1 and minimize T2. It's not clear what the maximum value of T1 could be, but we can make T2 equal to 0 to minimize that. That's what we do. We put T2 equal to 0. And that gives us a value of T1. We use that in the first equation to find the corresponding value for F. Does this make sense?
Yes, sir.
No problems on this?
No, sir.
Now, that's one way to think about this. Now, you might be thinking, how can tension be equal to 0? Right? How can the value of tension be 0 in something like this? Another way to think about this could be using the diagram, right? Another way to think about this could be using the diagram. And that will also help you understand how we can put T2 equal to 0. Let's have a look at this diagram instead. Let's have a look at this diagram and see, okay, we are looking for the greatest possible value of F, such that it remains in equilibrium, position like this. Now, what would happen if the equilibrium was to be broken, if the object was to start moving? Think about it. When the object comes here, for instance, after moving, this is how the string from A is going to be connected. And what about B? This was a much longer string. Now this block is closer to B. This string is going to be slack like this now. It's not going to be straight anymore. So when the object does move, the tension in string B is going to become 0 because it's not taut anymore. This string is now slack. So it can't really apply any force on this object. So tension in the second string becomes 0 when the object moves towards the right side. Now, when you apply this force F on the right side, when you're applying this force F on the right side, this force, if you keep increasing this value, to balance that force F, what happens is T1 keeps getting larger because there's going to be more pressure on at the point A. As you pull the block towards the right side, this point A is going to be under more pressure, right? The string coming from point A is going to be under more pressure. There's going to be more force on that side. And the tension in this part of the string is going to keep getting lower because of that, because a lot of that weight is now being countered by this force F. Okay. I'm sorry, it moved again. So what happens is, just when the object is about to move, so when this force F becomes large enough that the object is just about to move to the right side, the tension in this string is going to become 0. When it's just about to move, the tension in this string is going to be 0. And that is when the object is going to start moving to the right side. So what's that extreme point where the block is in equilibrium in the same position? That is when the tension in the second string basically becomes 0. That is when the object is going to start moving to the right side. So from the diagram as well, you could argue it like this, that as you keep increasing the force F to the right side, eventually, when the object is just about to move, the tension in this second string is going to become 0. And that is the point where the equilibrium position is going to break. So when you put T2 equal to 0, therefore, in these equations, that is when you're going to get the maximum possible value of F in this case. Okay, so that's how you could think of it using the diagram as well. Any problem with this? Any questions?
Sir,
No
with
problem?
the second
Yeah.
method that you said, where the string isn't taut anymore, the angle would change as well then if
The angle
length
would,
of the
yes.
changes.
Yeah, so we're not saying that the object is moved already. We're saying the object is just about to move. When it's just about to move, the string is still straight, but it's not applying any force anymore. So the object is not moved yet. We want the maximum possible value of F such that the block has not moved yet. Okay. So just
Okay,
at that moment, when the object is just about to move, the tension has already become 0, even though the string is straight at this point. That is when the object is just about to move now. So that's the greatest value of F. In that case, block is not moved yet. So the angles are still the same. Nothing else has changed. Just the tension has become 0 for that.
okay, sir.
Okay. All right. So that's one question that I wanted to do. Now let's have a look at the other one quickly. That's very similar. Take a minute to read the question statement, then we'll do it. Okay. So it says a block of mass 5 kilograms is held in equilibrium near a vertical wall by 2 light strings and a horizontal force of magnitude x Newton. The two strings are both inclined at 60 degrees to the vertical. Given that x equals 100, find the tension of the lower string. Now, the first part is relatively straightforward. Again, you're given the value of x already, that's 100 Newton. And you're given that the state is equilibrium. You need to find the tension in the lower string. The angles are also given. So let's quickly do the first part first. What are the forces acting? Let's represent the forces first of all. We have the weight of the block acting, that's downwards. Mass is 5 kilograms. That means the weight is 50 Newton. The force acting towards the right is 100 Newton. There's one tension that's going to act here. Let's call that T2 and T1, the force that's acting above. These are the two tensions that we have. And that's it. These are all the forces acting. 100 is already horizontal. 50 is already vertical. What about the components of these two forces? T1 is going to have one component upwards and one component towards the left. We can represent those two components, one component in this direction, one component vertically upwards. If this angle is 60, that means this angle here is also going to be 60. That gives us T1 cos 60 as the vertical component, and the component acting towards the left side, that is going to be T1 sine 60. Okay. These are the components of T1. What about T2? If this angle is 60, this angle here is also 60, alternate angle. Again, there are going to be two components of the force 60 of the force T2, one acting towards the left side. That is going to be T2 sine 60, and one acting vertically downwards, and that's going to be T2 cos 60. Again, you make two equations using this. We have these horizontal forces and we have these vertical forces. Just equate the opposite forces, right? Equate the forces acting towards the left side to the forces acting towards the right side, and equate the upward forces to the downward forces. Why? Because we have equilibrium. What are the forces acting towards the left side? T1 sine 60 plus T2 sine 60. Towards the right, we have 100. That's one equation. Upwards force is T1 cos 60. And the downward forces are 50 and T2 cos 60. Okay, so we just made these two equations. Now we solve them simultaneously. Sine 60 is under root 3 over 2. So we have under root 3 over 2 into T1 plus under root 3 over 2 into T2. That equals 100. We can simplify this by multiplying the whole equation by 2. That gives us under root 3 T1 plus under root 3 T2 equal to 100 times 2. That's 200. And then we could actually simplify this further by taking under root 3 common and dividing it on the other side. That will leave us with T1 plus T2 equal to 200 over under root 3. Okay, that's one equation that we have. Let's do this. Let's simplify the other one as well. T1 cos 60. Cos 60 is 1 over 2. So we have 1 over 2 T1 equals 50 plus cos 60 into T2. That's 1 over 2 times T2. Again, we can multiply the whole equation by 2 to get T1 equal to 100 plus T2. That's the other equation. Now we can just solve them simultaneously. What are we looking for? The question asks us to find the tension in the lower string only, right? So that's the only tension that we need, tension in the lower string. That's T2. So what we can do is we can eliminate T1. We already have that here. We can put that thing in the first equation. What does that give us? T1, 100 plus T2, that's the value of T1, and then plus T2, this T2, equals 200 over under root 3. And you can see what the value of T2 turns out to be from this. Let me check that. 2T2 equals 200 over under root 3 minus 100. What's the value of T2 that we get? So I'm getting 7.735 Newton. That's the value of T2 that we get in the first part, right? Pretty straightforward. Just equate the opposite forces and you find that tension. If you wanted to find T1 as well, you would put that in the second equation, and that will give you the value of T1 as well, but that's not needed. We only needed the tension in the lower string. So we're done with that. Now the second part says, find the least value of X for which the block remains in equilibrium in the position shown. Now, in the previous question, we were looking for the greatest value of a force. Now we're looking for the least value of a force. Now, in this case, for instance, we saw that here. We were looking for the greatest possible value of F such that the equilibrium position would change. Why? Because if F was too big, the block will move toward the right side. If it was too small, it would stay the same. In this case, however, We are looking for the least value of this force X. Now think about it. Let me actually just copy this first, this diagram. So again, we've resolved all the forces already. And the second part now, 100 Newton that they gave in the first part, that's no longer relevant, right? Because that was only for the first part. Now they're asking us to find the least possible value of X such that the block remains in equilibrium in this position. Now, if X was too small, if X was 0, let's say, what would happen? The block will fall down like this. It'll come here, right? Because it's in vertical position. Weight is going to make it go like this, in this direction, right? This X Newton force that is acting towards the right side, that is what is holding this block in this position. Okay. How do we find the least possible value of X in this case? Again, we still have equilibrium. So these equations that we wrote in the first part, they are still relevant. I'm going to copy those equations here again. Those equations from the first part, they are still relevant because the opposite forces are still equal. So again, we can think of it using these equations, first of all, that how can we minimize the force X? Now, we don't have 100 Newton here anymore. In place of that, we have X, right? So I'm just going to replace this with X now. X equals this and X equals this. And I can just leave it like this now. This is what we got above already, that X equals the sum of these two forces, okay? And then upwards and downward forces, they give us the same thing as before. This is what we're getting by equating upwards and downward forces. These equations still hold like before. Okay, just 100 is replaced with X now. Now what we want to do is we want to minimize the value of X. So we want X to be as small as possible. Okay, X needs to be as small as possible. How can we make X small? Now we have both positive terms here. How can we make X small? We would want T1 to be minimum and T2 to be minimum. We want both to be as small as possible. As small as possible, right? Now, what could be the smallest value that we can think of? We might think of, yeah, yes, Joseph, you're saying something?
So I was gonna say 0, but then
0?
X wouldn't be a
Yeah.
force. Why would it?
Yeah. So let's think about that. So let's think about making both of them 0, right? That's the least value that we can think of. We could make T1 0 and we could make T2 0. We could make both of them 0 like this, right? But that's going to be a problem, because if we put these in the second equation, we get 0 equals 100 plus 0, and that does not make sense. That means this is not possible, because T1 has to be equal to 100 plus T2. So T1 has to be 100 more than T2, right? That's what we're getting from the second equation. So making both of them 0 is not possible. Why? Because the second equation actually tells us that T1 minus T2 should equal 100. The difference of T1 and T2, that has to be 100. So both of them cannot be 0. Now, since the difference has to be 100, one possibility could be, for instance, T1 is 150 and T2 is 50, right? The difference is 100. It could be that the first one is 120 and this is 20. That is possible, right? 120 minus 20, that gives us 100. Now, since we want to minimize both of them, how do we minimize both of them such that the difference is also 100? Yes?
We can make one 101 and the other just 1.
Okay, so we can say T1 is 101 and T2 is 1. Why not 0.1? Is 1 the smallest number you can think of? It could also be 0.1, right? Then this is 100.1. Then what about 0.01? And this would be like 100.01. And what about 0? Why can't we make it 0? We can make T2 equal to 0 and T1 equal to 100. So the least value of T2 could be 0 in this case. We could make T2 equal to 0. And then the other force would be 100, and the difference would still be 100. The second equation will still hold true. So again, using these equations, what we figure out is, if we were to make T2 equal to 0, so for x to be minimum, T2 should be 0 in this case. And now if T2 is 0, put that in both equations. What do you get from that? If you put that in both equations, from the second equation, you get T1 minus 0 equal to 100 and T1 equals 100. Put that in the first equation now. You get under root 3 over 2 times T1, which is 100, plus under root 3 over 2 times T2, which is 0, that equals x. And that will give you the least possible value of x. In this case, that's under root 3 divided by 2 multiplied by 100. That's giving me 50 under root 3. That's 86.6 Newton. This is the least possible value of x. This is the least possible value of x, 86.6 Newton. Is that okay?
Yes, sir.
Does this make sense to everyone? Others? What do you think? Any questions? Any questions on this?
No, sir.
No. Now we could also think of this using the diagram. How would we do that? If the equilibrium position was to change, where is the block going to move? The block is going to move in this direction. And when it moves in this direction, what is going to happen to T2? The lower string is going to become slack when the block comes here, for instance. This will be straight, but this will be slack like this. This tension in the lower string is going to become 0. When the object is just about to start moving here, if x was too small and the block was just about to start moving downwards, the tension in the lower string is going to become 0. So you could just make T2 equal to 0 here by looking at the diagram that, okay, if it was just about to move downwards, the tension in the lower string would be 0. You put that equal to 0 in those equations, find the corresponding value of T1 from that, and that will give you the value of x as well. So again, you could think of it using this diagram as well, like this. So generally, in problems like these, when you have tension involved and you are looking for the least value of something or the greatest value of something, what you have to do is, so you understand this logic now, right? You understand how this logic works using the equation and also using the diagram. But now if you are kind of confused in the exam that, okay, what are we going to do in this case? How are we going to find the least value or the greatest value? One thing that you can remember is, when you have tensions involved like this, and you have a block, when you have some object hanging in equilibrium, in order to find least value or greatest value of something, what you have to do is, you have to put one of the tensions equal to 0. And that will give you that least value or greatest value. So some tension has to be put equal to 0. And then you can figure out which one of them can be put 0, which one is not possible to be 0. For instance, in this case, if T1 was 0, the block would just fall down. So T1 cannot be made 0. The only possibility is we'd make T2 0 because then X can handle the rest of it. T1 cannot be 0 because the only thing that's countering this weight of 50 Newton is T1 cos 60. So T1 cannot be made 0, T2 can be made 0. So just put T2 equal to 0. So that's a way to kind of remember this. Similar in the other equation, you can see this force acting towards the right side, force F, that is being countered only by T1 cos 36.87. Weight is being counted by both of these tensions. So if one of them becomes 0, the other can handle it. However, force F is being counted only by T1. So T1 cannot be 0, but T2 can be 0 in this case. So we make T2 equal to 0. So in problems like these, when you have to find least value of something or greatest value of something, that is what you have to do. You have to put one of the tensions equal to 0. And you can kind of logically think of which of them can possibly be 0 and which of them cannot be 0. The one that can be made 0, just put that equal to 0. In the friction, in another question, we had to find least value of some force. When you have a surface involved and friction involved, in that case, in order to find least value or greatest value, what you do is you consider limiting equilibrium. And in case of tensions like this, in case of a hanging object, when you have to find least value or greatest value, you consider one of the tensions to be equal to 0. So that's kind of something that you can remember now. For finding greatest or least values of any forces when the object is on a rough surface having friction, consider using limiting equilibrium. Limiting equilibrium will give you those extreme values of the forces, least force or greatest force. And if the object is hanging from some strings, consider putting one of the tensions equal to 0. That is going to give you the least value of a force or the greatest value of a force. All right, so it says the diagram shows a block D of mass 100 kilograms. And it's supported by two sloping struts, AD and BD. AD and BD, okay. Each attached at an angle of 45 degrees to fixed points A and B. अच्छा, यहाँ पे एक important information आपके पास आ गई 100 kg. वो आपको diagram पे भी नजर आ रहा है. That's okay. 45 degrees के angles भी नजर आ रहे हैं. Horizontal floor. The block is also held in place by a vertical rope CD. So you have this vertical rope here. Attached to a fixed point C. The tension in the rope CD is 500 Newton. And the block rests in equilibrium. Okay, सारी information आपको diagram पे नजर आ रही है. The key thing here is that the block rests in equilibrium. Okay, equilibrium वाली state है. Opposite forces equal होंगे. Left वाली force right वाली force के equal होगी. इस case के अंदर upward forces downward forces के equal होंगी. It says find the magnitude of the force in each of the struts AD and BD. ओके अब देखिए उसने each of AD and BD का है. इसका मतलब है इनमें जो फोर्स होगी वो डिफरेंट होगी. ओके इनमें फोर्स डिफरेंट होगी. तो अगर आप इस ब्लॉक को कंसिडर करें, दरम्यान वाला ब्लॉक है, इस ब्लॉक के ऊपर कौन कौन सी फोर्सेस लग रही हैं, लेट्स थिंक अबाउट दैम. इस ब्लॉक के ऊपर एक अपवर्ड फोर्स लग रही है 500 न्यूटन. एक इसका वेट है 100 kilograms is the mass. तो वेट कितना होएगा? There's a weight of 1000 Newton that's acting vertically downwards like this. ठीक है. अब इनफैक्ट ये सेम एंगल के ऊपर है तो ये सेम ही होनी चाहिए यार. एडी और बीडी के अंदर सेम ही आपकी होनी चाहिए बिकॉज ये एंगल सेम है. तो दोनों के अंदर टेंशन जो है उसकी वैल्यू भी सेम ही आनी चाहिए. या दैट मेक्स सेंस. अगर एंगल डिफरेंट होता है यहाँ पे तो फिर इसकी टेंशन डिफरेंट हो सकती थी. ओके बिकॉज ये फिक्स्ड पॉइंट के साथ अटैच्ड है. तो फिक्स्ड पॉइंट के साथ अटैच्ड होते हैं तो आपके टेंशन की वैल्यू डिफरेंट आ सकती है. लेकिन अगर एंगल डिफरेंट, अगर एंगल इक्वल है तो फिर आपकी वो वैल्यू सेम ही आ रही होती है. तो टेंशन हमारे पास है, एक इधर को ऐड कर रही है और एक इधर ऐड कर रही है. These are the two tension values that we have. Now, those of you have done Lamy's theorem, make sure that you do not use that here because you have 4 forces here. We don't have 3 forces, we have 4 forces. Lamy's theorem 3 forces के लिए use होता है sir. That makes things a lot easier a lot of times, but यहाँ पे वो use करने की जरूरत नहीं है. आप देखें वर्टिकल फोर्सेस इक्वल होनी चाहिए ऑफ कोर्स. तो जो नीचे की तरफ फोर्स लग रही होगी टोटल वो अपवर्ड फोर्स के इक्वल होगी. अपवर्ड फोर्स हमें पता है 500 न्यूटन है. डाउनवर्ड फोर्सेस कौन सी हैं? वी हैव 1000 न्यूटन एक्टिंग downwards. That doesn't quite make sense because this is 1000, or yeah, so maybe it's applying a force in the upwards direction. That is possible. Let's do that. इसको हम सॉल्व करते हैं पहले. अब अभी ब्लॉक के पर्सपेक्टिव से देखें. रिमेंबर हम जनरली क्या करते होते हैं? जनरली तो हम यही करते हैं कि हम डायरेक्शन जो लेते हैं टेंशन की, वो ऑब्जेक्ट से अवे लेते हैं. जिस ऑब्जेक्ट की बात करें उस ऑब्जेक्ट से अवे टेंशन लेते हैं. सो हम नीचे की तरफ डायरेक्ट टेंशन दे रहे हैं यहाँ पे. तो इसको हम देखते हैं टेंशन को रिजॉल्व करके क्या वैल्यूज आती हैं. राइट साइड वाली टेंशन को रिजॉल्व करते हैं. तो एक हमारी नीचे को लग रही होगी, एक कंपोनेंट यहाँ पे. दिस इज 45 डिग्रीज, रिमेंबर. सो वी हैव टी cos 45 here. तो साइन भी कर सकते हैं इसमें 45 here, doesn't make any difference. एक फोर्स यहाँ पे लग रही है, और इसी तरह जो दूसरी टेंशन है उसका भी जो कंपोनेंट नीचे को लग रहा होगा वो भी उतना ही होगा. दिस कंपोनेंट इज आल्सो t cos 45. नीचे वाले कंपोनेंट्स हैं. एक कंपोनेंट राइट पे लग रहा होगा, एक लेफ्ट पे लग रहा होगा, वो भी दोनों t cos 45 है. वो तो एक दूसरे को कैंसिल आउट करें, उससे हमें कोई इन्फॉर्मेशन नहीं मिलेगी. वहां से टी कैंसिल हो जाएंगे. सो दैट्स नॉट हेल्पफुल. लेकिन अपवर्ड फोर्सेस और डाउनवर्ड फोर्सेस को हम इक्वेट कर सकते हैं उस ब्लॉक के ऊपर. अपवर्ड फोर्सेस को डाउनवर्ड फोर्सेस से इक्वेट कर दें. अपवर्ड फोर्स क्या है? 500 न्यूटन. इक्वेट दैट टू द डाउनवर्ड फोर्सेस. डाउनवर्ड फोर्सेस हमारे पास कौन सी आ रही है? एक 1000 न्यूटन है प्लस t cos 45 plus t cos 45. These are the forces that are acting in the downward direction. Okay, so now I get this. यहाँ पे देखें, एक चीज मैंने यहाँ पे मिस कर दी. यहाँ पे उसने लिखा हुआ है, I was just thinking कि ये हो कैसे सकता है. So the confusion that is ये 500 न्यूटन देखें ऊपर को लग रही है ना फोर्स, और नीचे ऑलरेडी 1000 वेट लग रहा है. तो टेंशन नीचे पे तो नहीं लग सकती. So this is actually not tension. You're not going to treat this as a string. यहाँ पे देखें उसने लिखा हुआ है, जो mass है it's supported by the two sloping studs. ये दो आपके पास रॉड्स टाइप शो हो रहे हैं, ये उसको सपोर्ट कर रहे हैं, यानी कि उसके ऊपर की तरफ फोर्स लगा रहे होंगे. जो टेंशन आपके अब जो टी की वैल्यू लग रही होगी इसके ऊपर की तरफ लग रही होगी. असल में ऊपर की तरफ लग रहा होगा. बट इवन इफ यू डिड नॉट रियलाइज दैट व्हाइल यू वर डूइंग दिस, दैट्स ओके, बिकॉज एंड पे आपके पास टी की वैल्यू नेगेटिव आ रही होगी. जब टी की वैल्यू नेगेटिव आ जाएगी, दैट विल मेक यू अंडरस्टैंड कि असल में डायरेक्शन ऑपोजिट होनी थी. सो इवन इफ यू एंड अप डूइंग इट लाइक दिस, दैट्स गोइंग टू बी ओके. इससे आप देखें आपके पास क्या आता है. 500 equals 1000. That's going to give you 500 minus 500 here. On the other side, you have 2t cos 45. Cos 45 is square root of 2 over 2. 2 and 2 get cancelled. Square root of 2 जाके वहां पे divide हो जाएगा. And that will turn out to be 500 divided by square root of 2. And that is minus 353.55 न्यूटन. अब यहाँ पे मेरे पास t की वैल्यू नेगेटिव आ रही है. इसका मतलब ये है कि जो असल में जो डायरेक्शन है t की ना, वो ऊपर की तरफ है. क्यों? क्योंकि ये इस ब्लॉक को सपोर्ट कर रहे हैं. ये जो रॉड्स हैं ये उस ब्लॉक को सपोर्ट कर रहे हैं, तो फोर्स असल में ऊपर को लगा रहे हैं. बट दैट्स ओके, इट डजंट मेक एनी डिफरेंस. उसने पूछा क्या था हमसे? उसने पूछा था मैग्नीट्यूड ऑफ द फोर्स इन ईच ऑफ दीस AD एंड BD. तो उनका मैग्नीट्यूड क्या होगा इस केस के अंदर? मैग्नीट्यूड ऑफ दिस फोर्स, that is 353.55. That's all that we are interested in. This is 353.55 Newton. Okay? ये आपको figure out करना था in the first part here. Let's move on and look at the next one. This was 5 part A. Part B. A horizontal force of magnitude F Newton is applied to the block in direction parallel to AB. Okay. Find the value of F for which the magnitude of the force in the start AD is equal to 0. Now, let me just copy this diagram here. So बहुत ज़्यादा clutter हो गया. आप क्या करेंगे एग्जाम में? ये पेंसिल से करेंगे जो आपने एनोटेट किया उसके ऊपर, ताकि फिर आप उसको इरेज करके नेक्स्ट पार्ट के लिए यूज कर सकें. I'm just going to copy that diagram here on the side. Okay, so this is what it looks like. ये आपके पास डायग्राम है. Okay. A horizontal force of magnitude F Newton is applied to the block in direction parallel to AB. तो एक फोर्स लग रही है यहाँ पे, let's say right side के ऊपर. अब देखिए सब कुछ सिमेट्रिकल है, आप इसको राइट पे अज्यूम करें या लेफ्ट पे अज्यूम करें, that is not going to make any difference. ठीक है, तो आप let's say राइट पे अज्यूम कर ले, राइट पे फोर्स लग रही है F Newton. Now find the value of F for which the magnitude of the force in the strut AD is equal to 0. Okay. अब देखिए जब ये राइट साइड पे फोर्स लगेगी इस तरह से, तो इस ब्लॉक के ऊपर एक राइट साइड पे प्रेशर आएगा. ठीक है, इसको बैलेंस करने के लिए आपको जो लेफ्ट पे फोर्स है वो कोई चाहिए उसको सपोर्ट करने के लिए, ताकि उसके लेफ्ट उसको काउंटर कर सके लेफ्ट पे. अब लेफ्ट पे फोर्स कहाँ से आ सकती है? वो जो ये वाला रॉड है ये उसको सपोर्ट कर सकता है उस साइड के ऊपर. ठीक है, ये उसको, क्योंकि रिमेंबर इसको पुश करें ना इस तरफ को, तो लेफ्ट पे जब एफ आप राइट पे लगाएंगे तो ये रॉड नीचे से उसको लेफ्ट पे सपोर्ट दे रहा होगा, तो उसको उसकी पोजीशन में रखेगा. अच्छा, अब let's just do that. जो उसने कहा हुआ है, उसने कहा है find the value of F for which the magnitude of the force in the strut AD is equal to 0. Now it's the block remains in equilibrium. It's not moving, right? So it's not supposed to move from this direction. अब इस केस के अंदर AD की वैल्यू अगर हम 0 कर दें, अगर AD का मैग्नीट्यूड हम 0 कर दें तो उससे क्या होगा वो हम देखते हैं. सबसे पहले इसको रिजॉल्व कर लेते हैं. इन दोनों में जो टेंशन है उनको रिजॉल्व कर लेते हैं. रिमेंबर अब टेंशन इक्वल नहीं रहेंगे बिकॉज आपकी वो सिमेट्री खत्म हो गई है. पहले सिमेट्रिकल था ना सब कुछ, एंगल्स भी 45 डिग्री थे, टेंशन दोनों की इक्वल आ रही थी. नाउ द टेंशंस आर नॉट नेसेसरली गोइंग टू बी इक्वल. तो ये ब्लॉक है, हम एज्यूम करते हैं उसी तरह से जिस तरह हम नॉर्मली करते हैं. लेट्स से दिस इज द डायरेक्शन ऑफ टेंशन हियर एंड दिस इज द डायरेक्शन ऑफ टेंशन हियर. अगर ऑपोजिट होगा खुद से नेगेटिव आ जाएगा, वी डोंट हैव टू वरी अबाउट दैट. ओके, ये आपके फोर्सेस कहते हैं. अब हम क्या करते हैं, इसको हम कह लेते हैं TA, इसको हम कह लेते हैं TB. What they want is that the tension in the force and in the strut AD is equal to 0. इसको आपने 0 से इक्वेट करना है. अब उससे पहले हम क्या करते हैं, सारी फोर्सेस को रिजॉल्व कर लेते हैं. एक TB आ रहा है, TB के कंपोनेंट्स क्या होंगे और TA के कंपोनेंट्स क्या होंगे, ये उसी तरह होंगे जैसे हमने पहले निकाले थे. एक कंपोनेंट यहाँ पे नीचे पे लग रहा होगा, TA cos 45, और इसी तरह आपके पास एक और होगा which is going to be TB cos 45. और आपकी साइड्स पे भी फोर्सेस लगी होंगी. एक आपका कंपोनेंट लेफ्ट पे लगा होगा TA का, that's going to be TA sin 45 if you're considering this as 45. और एक कंपोनेंट इसका भी राइट पे लगा होगा TB का, which is going to be TB cos 45. ठीक है, but don't forget that weight as well. एक आपका वेट लग रहा है नीचे की तरफ, that is 1000 न्यूटन, that is also going to be there. ये आपकी सारी फोर्सेज हैं इसके ऊपर लग रही हैं. आप क्या करें, आप देखें हॉरिजॉन्टल फोर्सेस कौन सी हैं. यू हैव TB cos 45 and you have F and you have TA sin 45. These are the horizontal forces. Okay. Vertical forces क्या हैं? Vertical forces are 1000 Newton, TB cos 45, TA cos 45 and 500 Newton. लेफ्ट वाली फोर्सेस राइट वाली फोर्सेस के इक्वल होनी चाहिए, अपवर्ड फोर्सेस डाउनवर्ड फोर्सेस के इक्वल होनी चाहिए. तो आप उनको इक्वेट कर दें. और करना क्या आपने, AD वाली जो टेंशन है उसको आपने 0 कर देना. ठीक है, उससे देखना आपके पास क्या आता है. हॉरिजॉन्टल देख लेते हैं, लेफ्ट वाली फोर्सेस को राइट वाली फोर्सेस के इक्वेट कर दें एंड सी व्हाट दैट गिव्स अस. लेफ्ट पे हमारे पास लग रहा है TA sin 45, बट रिमेंबर TA की वैल्यू तो 0 है. TA तो हमने 0 इनपुट करना है तो उसको 0 कर देंगे. On the right side we have F plus TB cos 45. Now this thing becomes 0 because उसने कहा होगा TA की वैल्यू 0 आपने लेनी है. This becomes 0 equals F plus TB into square root of 2 divided by 2. ठीक है, and then we have the vertical set of forces, एक तो आपके पास ये आ गई इक्वेशन, इससे हम ऑफ कोर्स f की वैल्यू भी नहीं निकाल सकते। हम क्या करते हैं, इसमें से tb को सब्जेक्ट बना लें ताकि हम उसको एलिमिनेट कर सकें दूसरी इक्वेशन से। अगर हम tb को सब्जेक्ट बनाते हैं तो क्या हो जाएगा, -2 over square root of 2, that's going to be square root of 2। तो इसको लिख लेते हैं एक दफा, -f उस साइड पे चला जाएगा, फिर आप 2 से मल्टीप्लाई करेंगे और स्क्वायर रूट ऑफ 2 से डिवाइड करेंगे। 2 over square root of 2 क्या हो जाएगा, स्क्वायर रूट ऑफ 2। तो आपके पास राइट साइड पे आ जाएगा इवेंचुअली -square root of 2 times f, दैट इज व्हाट tb इज इक्वल टू। ठीक है, ये एक इक्वेशन से आपके पास आ गया, लेफ्ट इक्वल राइट करने से आपके पास ये आ गया। नाउ इक्वेट द अपवर्ड्स एंड डाउनवर्ड फोर्सेस एंड सी व्हाट यू गेट फ्रॉम दैट। This is equation 1. Upward and downward forces को equate कर दें। Upward force is 500, downward is TA cos 45 plus TB cos 45 plus 1000। ठीक है, अब अगेन TA की वैल्यू उसने क्या कहा हुआ है, 0 है, अब इसको 0 कर दें। So what are we left with, 500 equals 0 plus TB into square root of 2 over 2 plus 1000. Now what you're looking for is the value for f. In fact, यहाँ से आपके पास TB आ जाएगा डायरेक्टली, आप TB की जगह पे ये डाल दें, however you want to do it, और आप देखें आपके पास क्या आता है। Left side पे I'm getting -500, on the right side I have square root of 2 over 2 times TB. Okay, now if I input that in place of TB, जो ऊपर हमने निकाला था, TB की वैल्यू क्या है, square root of 2 times f. Let's input that, minus square root of 2 times f. वो input कर दें इसके अंदर। Now that gives us -500 equals -2 over 2 times f, and f turns out to be equal to 500 Newton. And that is what we were looking for here. This is the value of f that we get if TA is equal to 0. All right. Now again, देखें, आपने उससे परेशान नहीं होना कि टेंशन की वैल्यू नेगेटिव आ रही है, ये पॉजिटिव आ रही है। आपने उसी तरह करना है जिस तरह आप नॉर्मली करते हैं, इवन दो टेंशन ऊपर को लग रही है, असल में ये थ्रस्ट है और ये ऊपर को लग रहा है, लेकिन आपने उसको उसी तरह करना है ट्रीट जैसे आप नॉर्मली करते हैं। जिस पॉइंट को आप देख रहे हैं उससे अवे अज्यूम करना है, उसकी वैल्यू नेगेटिव आ जाएगी खुद से, एंड दैट्स ओके। ऑलराइट, थ्रस्ट को अलग से कंसिडर करना, दैट्स नॉट पार्ट ऑफ योर सिलेबस। You won't get a more complication than that. आप जिस तरह से टेंशन से डील करते हैं, आपने उसी तरह से टेंशन से डील करना है। बस जस्ट रिमेंबर कि उसकी वैल्यू नेगेटिव आ सकती है कभी कभी, एंड दैट्स ओके। जब आपकी स्ट्रिंग जो है वो रिजिड होती है, कोई रॉड होता है, तो उसकी वैल्यू नेगेटिव आ सकती है, एंड दैट्स एक्सेप्टेबल। ओके, नेक्स्ट वन। नाउ इट सेज a ring of mass 4 kg is threaded on a smooth circular rigid wire. Rigid wire आपके पास आ रही है। रिमेंबर, रिजिड वायर जो होती थी, तो हमारे पास अगर उस पर कोई ऑब्जेक्ट है तो अगर उसके साथ कनेक्टेड होता है तो एक तो उसमें टेंशन की वैल्यू नेगेटिव भी आ सकती थी। रिमेंबर, एक वो इसमें होता है रिजिड वायर का केस, तो आपको याद रखना होता है, क्योंकि वो उसमें एक तरह से थ्रस्ट आ जाता है, तो वो एक चीज होती है जो आपने ध्यान में रखनी है। बट लेट्स सी व्हाट इट सेज। रिंग का मास 4 kg है। दिस इज द रिंग दैट यू कैन सी हियर। सेंटर C है उस वायर का, we have this wire, इसका सेंटर C है। The wire is fixed in a vertical plane and the ring is kept at rest by a light string connected to A. Okay, so ये ring है, ये इसके साथ एक string attached है that is connected to this point A. It's like this, right? ये string है जो आपको ऊपर नजर आ रही है और उससे A से connect किया हुआ है। Now the ring is kept at rest. Okay, so it's kept at rest, it means there is equilibrium. Okay, the opposite forces होंगी वो equal होंगी, left वाली force right के equal, upward force downward force के equal. Keep that in mind. The highest point of the circle is A. वो आपको नजर आ रहा है। The string makes an angle of 25 degrees to the vertical. Find the tension in the string. Okay, tension in the string. Tension कहाँ पर होगी? ये आपकी ring है, string किधर है? ये आपकी string है। Tension acts away from the point of reference. अगर आप ring की बात करें, ring से away लगी होगी tension, that's going to be in this direction. This is the direction of the tension. Okay. Now, the second thing that they ask about is find the magnitude of the normal reaction of the wire on the ring. अच्छा देखें, वायर के ऊपर ये रिंग एक तरह से रिंग जो है वो वायर के ऊपर थ्रेडेड है, राइट? अब वायर के साथ कनेक्शन होएगा जब कोई भी दो ऑब्जेक्ट्स कनेक्ट होते हैं एक दूसरे के साथ, दो फोर्सेस होती हैं आपके पास। कॉन्टैक्ट फोर्सेस क्या होती हैं? फ्रिक्शन होती है, और आपके पास दूसरी होती है रिएक्शन फोर्स। उसने कहा ये वायर तो स्मूथ है, फ्रिक्शन तो नहीं है, तो रिएक्शन तो होगा, लेकिन अब रिएक्शन किस डायरेक्शन में लगेगा? रिमेंबर, रिएक्शन ऑलवेज एक्ट्स परपेंडिकुलर टू द सर्फेस, whatever the surface is. In this case, the surface is this circular wire. अब इस पॉइंट के ऊपर जहां पे वो उस रिंग के साथ कनेक्टेड है, उस पे जो सरफेस की डायरेक्शन होगी उसके परपेंडिकुलर आपका रिएक्शन लग रहा होगा। नाउ व्हाट्स द डायरेक्शन ऑफ द सरफेस एट दिस पॉइंट? सरफेस की डायरेक्शन वो है जो इस पॉइंट पे अगर आप टेंजेंट बनाते हैं, जो इसकी डायरेक्शन होती है, दैट्स द डायरेक्शन ऑफ द सरफेस, राइट? दैट्स द डायरेक्शन ऑफ द सर्कल एट दिस पॉइंट। तो उसके परपेंडिकुलर आपका रिएक्शन लगना है। परपेंडिकुलर उसके क्या होएगा? द लाइन दैट इज गोइंग टू द सेंटर ऑफ द सर्कल, राइट? रिमेंबर, टेंजेंट और रेडियस परपेंडिकुलर होते हैं एक दूसरे के। यहाँ पे जो रिएक्शन लग रहा होगा वो इस पॉइंट से सर्कल के सेंटर की तरफ लग रहा होगा। दिस इज गोइंग टू बी द डायरेक्शन, राइट? बट नाउ you have to think about whether this reaction is acting in this direction, which is possible. Perpendicular लगना है ना, तो या तो एक डायरेक्शन ये हो सकती है, ये भी पॉसिबिलिटी है कि इसके ऑपोजिट लग रहा हो इस डायरेक्शन के अंदर। वी डोंट नो विच ऑफ दीज टू डायरेक्शंस इट्स गोइंग टू बी। वो एक तरह से रिएक्शन जो होता है ना, वो एक बैलेंसिंग फोर्स होता है, बाकी फोर्सेस पे डिपेंड करता है, बाकी फोर्सेस किस डायरेक्शन में ज्यादा हैं। अगर तो ऊपर वाली डायरेक्शन में ज्यादा फोर्सेस हैं तो रिएक्शन नीचे को लग जाएगा, अगर नीचे वाली डायरेक्शन में ज्यादा फोर्सेस हैं तो रिएक्शन ऊपर का लग जाएगा इस डायरेक्शन में। सो वी आर नॉट श्योर अबाउट दैट। इट्स गोइंग टू बी वन ऑफ दीज टू डायरेक्शंस, या तो सर्कल की तरफ लग रहा, सेंटर की तरफ लग रहा होगा, या फिर सेंटर से अवे इधर लग रहा होगा। अच्छा, वो भी हम देखते हैं कि कौन सी डायरेक्शन होगी। लेट्स रिप्रेजेंट द अदर फोर्सेस फर्स्ट ऑफ ऑल। रिंग के ऊपर और कौन सी फोर्सेस लग रही हैं? एक तो टेंशन होगी, देयर इज वेट एज वेल, राइट? वेट ऑलवेज एक्ट्स वर्टिकली डाउनवर्ड्स, एंड दैट्स गोइंग टू बी इन दिस डायरेक्शन। 4 kg is the mass, weight is going to be 40 Newton. अब रिएक्शन डिपेंड करता है कि ये जो 40 का कंपोनेंट है इस डायरेक्शन के अंदर, वो भी हम देखते हैं कैसे निकालेंगे, और जो टेंशन का कंपोनेंट है इस डायरेक्शन के अंदर, उनमें से कौन सी बड़ी फोर्स है। तो अगर तो टेंशन का कंपोनेंट बड़ा है वेट के कंपोनेंट से, तो फिर रिएक्शन नीचे को लग रहा होगा, और अगर वेट का कंपोनेंट बड़ा है टेंशन के कंपोनेंट से, तो फिर रिएक्शन ऊपर को लग रहा होगा। नाउ वी डोंट नो व्हाट which one of these two cases it's going to be, because the tension that we have is unknown. टेंशन हमें पता नहीं है, वेट पता है लेकिन टेंशन नहीं पता, तो हमें नहीं पता टेंशन बड़ी है या वेट बड़ा है। ओके, तो रिएक्शन जो है या तो इधर होगा ऊपर की तरफ, या इधर होगा, इसमें से कुछ भी हो सकता है, हमें नहीं पता। आप क्या करेंगे, कोई भी एक डायरेक्शन एज्यूम कर लें, ऊपर की तरफ कर लें, नीचे की तरफ कर लें, इट डजंट मैटर। अगर असल में जो डायरेक्शन है वो उल्टी है, तो एंड पे आपको आर की वैल्यू नेगेटिव मिल जाएगी, और फिर आप कहेंगे कि अच्छा असल में डायरेक्शन उल्टी थी, तो वो आप उसको बस साइन चेंज कर देंगे एंड दैट विल गिव यू द करेक्ट रिजल्ट। ओके, तो उससे फर्क नहीं पड़ता, आप किसी भी एक डायरेक्शन में ले लें, ठीक है। ऊपर टी भी लग रहा है वहां पे, उसका भी हमें वो करना होगा, कंपोनेंट्स निकालने होंगे, तो क्लटर थोड़ा ज्यादा हो जाएगा। मैं इधर नीचे की तरफ कर लेता हूँ, ऊपर की तरफ कर ले, नीचे की तरफ कर ले, डजंट मैटर। एंड पे आपको जो आंसर आएगा ना उससे पता चल जाएगा, नेगेटिव आएगा तो उसको पॉजिटिव कर देंगे बस, ठीक है। अच्छा, नाउ लेट्स फाइंड द एंगल्स दैट वी हैव। ये फोर्सेस तो आ गए आपके पास, अब एंगल्स देखते हैं, क्योंकि हमें अब इन फोर्सेस को रिजॉल्व करना है। हाउ डू वी रिजॉल्व दीज फोर्सेस नाउ? Weight is already acting vertically, we don't have to do anything with that. टेंशन और रिएक्शन को रिजॉल्व करने के लिए अब एंगल्स देखने पड़ेंगे। लेट्स थिंक अबाउट दोस एंगल्स नाउ। दिस इज 25 degrees. ओके, दैट्स वन एंगल दैट वी आर गिवन। अगर हम रिंग के साथ देखें, तो अगर इसी वर्टिकल लाइन इस तरह बनाते हैं ऊपर को, दिस एंगल इज गोइंग टू बी 25 degrees as well, राइट? तो टेंशन के कंपोनेंट्स तो हम इस एंगल को यूज करके निकाल सकते हैं, ठीक है। और व्हाट अबाउट रिएक्शन? रिएक्शन के साथ क्या एंगल लग रहा होगा वो हमें देखना पड़ेगा। what we can do is we can draw this, extend this line to the center of the circle and then see कि angles आपके पास क्या आ सकते हैं. Yeah, so it's an isosceles triangle, right? So this is 25 degrees. If this is 25, then this angle here is also going to be 25, right? And if this is 25, what are we left with here? बाकी angle कितना बचा यहाँ पे? 50 हो गया, total 90 था ये, right? तो आपके पास ये angle हुआ 40 degrees. And if this angle is 40, ये जो लेफ्ट पर हमारा एंगल बन रहा होगा इस डायरेक्शन के अंदर, this is also going to be 40, right? Vertically opposite angles. ये वाला एंगल भी कितना होएगा? ये भी 40 डिग्रीज होएगा. अब इसको यूज करके हम R को भी क्या कर सकते हैं? उसके कंपोनेंट्स भी निकाल सकते हैं. ठीक है, let's find the components now. इसके लिए मैं डिफरेंट कलर्स यूज कर लेता हूँ, doesn't really matter. टेंशन के कंपोनेंट्स निकाल ले. टेंशन का कंपोनेंट ऊपर की तरफ, एंगल के एडजेसेंट क्या लग रहा होगा? Cos, so we have t cos 25 here. Angle के दूसरी साइड पे, that's going to be t sin 25. ठीक है. अच्छा, अब रिएक्शन को देख लें. 40 डिग्रीज के एडजेसेंट कंपोनेंट, that is going to be r cos 40 degrees. और फिर नीचे वाला कंपोनेंट क्या आएगा? It's going to be r sin 40 degrees. ठीक है. These are the components that we have. अब इनको इक्वेट कर दें, लेफ्ट वाली फोर्स राइट वाली फोर्स के इक्वल, अपवर्ड फोर्स डाउनवर्ड फोर्स के इक्वल, and that is going to give you the result. Okay, let's do that now. Equilibrium है, right? ये रेस्ट के ऊपर है, तो we say let's equate the force acting towards the left to the force acting towards the right, and also equate upward forces to downward forces. Opposite forces equal होनी चाहिए. Left पे forces कौन सी हैं? इनको हम यहाँ पे highlight कर लेते हैं. We have r cos 40 acting towards the left. Right पे we have t sin 25, and vertical forces are t cos 25 here, 40, and r sin 40. Let's equate the opposite forces. Left पे we have r cos 40. On the right side we have t sin 25. That's one equation that we have. Upwards forces t cos 25. Downwards is r sin 40 plus 40. These are two equations that we have. All we have to do is solve these two equations simultaneously, and that is going to give us our result. Okay, हम क्या करें अब? इसमें हम एक equation में से किसी को subject बना लेते हैं. Let's make r the subject here. If we do that, we get t sin 25 over cos 40. Let's put that in the other equation. R की जगह पे ये input कर दें. So we have t cos 25 equals r, which is t sin 25 divided by cos 40 whole multiplied by sin 40 plus 40. अब इसको evaluate कर लें और अब देखें right side पे क्या आता है. So we have t cos 25 equal to something here. Let's see what this is. Sin 25 divided by cos 40 into sin 40 plus 40. All right, and that's giving me 40.355 on the right side. Now divide cos 25 on the other side and see what that gives us. Divided by cos 25, and that turns out to be 44.5 for me. Okay, let me just check my working again. If it's correct, maybe something missing here. Okay, so we have t cos 25, that is fine. यहाँ पे हमने कोई error तो नहीं किया है. अच्छा, t sin 25 divided by cos 40, t cos 25 that equals this into sin 40 plus 40. Achha, I need to check my calculation again. Sin 25 कैलकुलेटर डिग्रीज मोड में है, डिवाइडेड बाय cos 40 into sin 40 plus 40 divided by cos of 25. Okay, actually there's something wrong with my calculation. I'm just not able to figure out where the problem is. Oh yeah, sorry about that. So there's a T on the right side as well, right? So I was missing that. I'm sorry about that. So this is a T here. That's I'm missing. I thought this whole thing to be a single number, right? Achha, let's simplify this. Right, left to right दोनों को simplify करना पड़ेगा. Left side में हमारे पास आता है cos 25. Cos 25 is 0.9063 multiplied by T. Right side में भी एक T आ रहा है. तो हमें फर्स्ट टर्म को अलग से सिंप्लीफाई करना है. इस पे देखते हैं हमारे पास क्या होता है. sin 25 divided by cos of 40 into sin of 40, and this turns out to be 0.3546 t plus 40. ठीक है, take t terms to one side. 0.9063 minus 0.3546, that's giving me 0.5517 times t equals 40, and the value of t therefore turns out to be 40 over this number, which is giving me 72.5 Newton. That's the value of t that it turns out to be. Okay, put this back in the other equation to find the corresponding value for r, and let's see what that is. R equals 72.5 into sine of 25 divided by cos of 40. Let's see what R turns out to be from here. 72.5 into sine of 25 divided by cos of 40. And that is 39.999. You can say that's 40.0 Newton. These were the two values that we were looking for, the value for R and the value for T. You have to find curly, and that's all that we wanted. It says a crate of mass 300 kilograms is at rest on a rough horizontal ground. So we have 300 kg mass given. It's a rough horizontal ground. That means there is going to be friction. The coefficient of friction between the crate and the ground is 0.5. So we have the coefficient of friction given. Mu, a force of magnitude x Newton acting at an angle alpha above the horizontal is applied to the crate where sine alpha is given to be 0.28. Find the greatest value of x for which the crate remains at rest. Okay, now let's think about this. Again, let's draw a horizontal surface here. So it looks like this. Let's draw this here. So we have this horizontal rough surface. On the surface, you have a crate of mass 300 kilograms at rest. So एक हम यहाँ पे box बना देते हैं. ये आपके पास एक mass उसके ऊपर पड़ा हुआ है. What's the weight of this block? This is 3000 Newton. Okay. Acha. Now what's happening is there's a force acting on this block at an angle of alpha above the horizontal. Uska magnitude kitna hai? X Newton. So let's represent that force here. So there's force acting here. This is X. The angle that we have with the horizontal axis here is alpha. Okay, usne sin alpha diya hua hai 0.28. This is the information that we have. Now we need to find the greatest value of x for which the crate remains at rest. अच्छा देखिए forces कौन-कौन सी लग रही हैं इसके ऊपर. पहले तो वो सारी लिख लेते हैं. It's a rough surface. So the forces that we have are weight. We have already represented that. That's acting downwards. We have reaction. That's going to be acting upwards. We don't know the value for that yet. Don't just assume कि वो 3000 है. It's not, because all भी forces आपकी हैं. So R is acting upwards. and what else? We have friction, right? आप x right side पे apply कर रहे हो तो friction कहाँ पे लगेगी? Left side के ऊपर, क्योंकि ऑब्जेक्ट को ये फोर्स x राइट साइड में मूव करने की कोशिश कर रही है, फ्रिक्शन उसको अपोज करेगी एंड फ्रिक्शन एक्ट्स पैरेलल टू द सरफेस, इट्स गोइंग टू एक्ट टू द लेफ्ट। ओके, ये हमने रिप्रेजेंट कर ली फ्रिक्शन यहाँ पे, ठीक है। नाउ व्हाट वी डू इज, उसने कहा है सबसे पहले तो हम इसको रिजॉल्व कर लेते हैं। वी हैव x हियर, x को रिजॉल्व कर लें, इसके कंपोनेंट्स क्या होंगे? वी आर गोइंग टू हैव अ हॉरिजॉन्टल कंपोनेंट हियर, दैट्स गोइंग टू बी x cos alpha and a vertical component which is x sin alpha, ठीक है। अच्छा देखें, जब मूवमेंट है ब्लॉक की वो वर्टिकली तो होगी नहीं, तो वर्टिकल फोर्सेस तो इक्वली होंगी, राइट। तो हम क्या कर सकते हैं, अपवर्ड फोर्स और डाउनवर्ड फोर्स को हम इक्वेट कर सकते हैं, ठीक है। अपवर्ड फोर्स क्या है? r, downward force and we also have x sin alpha, and the downward force is 3000. So we have one relation between r and x. From this we know the value for sin alpha, we can put that here, this is 0.28. This is one equation that we have, okay। अब उसने कहा है find the greatest value of x for which the crate remains at rest। अच्छा देखें क्या होगा, आप x एक फोर्स लगा रहे हो, अब अगर ये बहुत थोड़ी फोर्स है, लेट्स से ये 10 न्यूटन फोर्स होती, अब ये इतनी थोड़ी फोर्स है इसके वेट के कॉरेस्पॉन्डिंग कि फ्रिक्शन मोस्ट लाइकली क्या करेगी, इसको अपोज कर लेगी और इस ऑब्जेक्ट को मूव नहीं करने देगी। आप इस फोर्स को बढ़ाते जाएं, लेट्स से 100 कर दें, 1000 कर दें, किसी पॉइंट पे जाके ये ऑब्जेक्ट मूव करना शुरू कर देगा, राइट। किसी पॉइंट पे जाके ये ऑब्जेक्ट मूव करना शुरू कर देगा। अब वो कौन सा पॉइंट है जिसपे वो बिल्कुल मूव करने लगा है? If you think about that, that's the limiting equilibrium वाली situation, right? Greatest value of x for which the crate remains at rest, तो ये वो वाला केस होएगा जब आपका limiting equilibrium है, because x की वैल्यू उससे थोड़ी सी भी ज्यादा होगी तो आपका ऑब्जेक्ट राइट पे मूव कर जाएगा। उसने कहा ग्रेटेस्ट वैल्यू ऑफ x for which the block remains at rest, तो बिल्कुल वो टिपिंग पॉइंट जहां पे अभी वो मूव करने ही लगा है, वो पॉइंट पे, उस पॉइंट पे हमें x की वैल्यू फिगर आउट करनी है। इन अदर वर्ड्स, वी वांट द वैल्यू ऑफ x व्हेन द ब्लॉक इज इन लिमिटिंग इक्विलिब्रियम, दैट्स व्हाट द सिचुएशन इज, ओके। तो हम क्या कर सकते हैं, क्योंकि हमने फिगर आउट कर लिया लिमिटिंग इक्विलिब्रियम वाला केस है, तो फ्रिक्शन की वैल्यू उसमें क्या होती है? फ्रिक्शन की वैल्यू उसमें म्यू आर के इक्वल होती है। सो हम इस केस के अंदर लेफ्ट वाली फोर्स और राइट वाली फोर्स भी इक्वेट कर सकते हैं, बिकॉज इक्विलिब्रियम है और लिमिटिंग इक्विलिब्रियम है, इनको इक्वेट किया। लेफ्ट वाली फोर्स कौन सी है? F, राइट फोर्स आपकी कौन सी लग रही है? x cos alpha, ठीक है। अच्छा अब क्या करें, फ्रिक्शन की जगह पे म्यू आर डाल देते हैं, बिकॉज सिंस इट्स लिमिटिंग इक्विलिब्रियम, जब भी लिमिटिंग इक्विलिब्रियम होता है, द फर्स्ट थिंग दैट शुड कम टू योर माइंड इज F equals mu r. Limiting equilibrium केस में फ्रिक्शन की वैल्यू mu r के इक्वल होती है। Now we know the value for mu. Mu is 0.5. इसने यहाँ पे क्वेश्चन में बताया हुआ है हमें। Okay, and we have x into cos alpha. Cos alpha हम फिगर आउट कर सकते हैं, आप यहाँ से बेशक वो निकाल लें, आप डायरेक्टली भी कर सकते हैं, इसके एग्जैक्ट वैल्यू भी निकाल सकते हैं if you want, using that rule that you've done in paper 1, या फिर इसमें उसने एग्जैक्ट वैल्यू तो नहीं पूछी आपसे, आप सिंपली क्या करें, अल्फा फाइंड कर लें और उससे फिर cos alpha निकाल लें, that's perfectly okay as well. So sin alpha is 0.2, आप क्या करें, अल्फा फाइंड करें, sin inverse is 0.28, make sure that you are writing a number of decimal places there ताकि आपके answers accurate रहें. Sin inverse of 0.28, that is giving me 16.2602. okay, अब मैं क्या करता हूँ, इसका cos alpha फाइंड कर लेता हूँ। cos of this angle, calculator value use कर लें, cos of this angle turns out to be 24/25, which is given me 0.96. okay, तो cos alpha की वैल्यू यहाँ पे इनपुट कर देते हैं, that is supposed to be 0.96. ठीक है। अच्छा अब म्यू की वैल्यू भी डाल दें, म्यू उसने दिया हुआ था 0.5. we have another equation in r and x, 0.5r equals 0.96x. इससे जो हमें x की वैल्यू मिलेगी वो ग्रेटेस्ट वैल्यू ऑफ x होगी, राइट, बिकॉज लिमिटिंग इक्विलिब्रियम हम कंसीडर कर रहे हैं, उससे थोड़ी सी भी ज्यादा होगी तो लिमिटिंग इक्विलिब्रियम ब्रेक हो जाएगा और वो ऑब्जेक्ट मूव करने लग जाएगा। लेट्स फाइंड द वैल्यू ऑफ x फ्रॉम दिस। हाउ कैन यू फाइंड दैट? वी कैन eliminate r from this, 0.5 जाके वहाँ पे divide कर दे. What is that going to give us? 0.96 divided by 0.5, that is 1.92. 1.92x. Put this in the other equation. And that gives us 1.92x plus 0.28x equals 3000. And you can find the value of x from this and see what that turns out to be. 1.92 plus 0.28, that is giving me 2.2. Now 3000 divided by 2.2. Let's see what that turns out to be. 3000 divided by 2.2, and that is giving me x equal to 1363.6. We can say 1364 Newton. This is our final answer. Okay. Okay. This is to 4 significant figures, which is perfectly okay. Minimum 3 होने चाहिए, 3 से ज़्यादा हो सकते हैं. Unless उसने question में कुछ कहा हो, यहाँ पे उसने question में कोई instruction नहीं दी है. You can leave it like this and that's okay. All right, so x, the greatest value of x turns out to be 1364 Newton, right? Okay, let's look at question number 3. Now, let's try this. It says the particle of mass 2.5 kilograms is held in equilibrium. This is also equilibrium. It's on a rough plane inclined at 20 degrees to the horizontal by a force of magnitude T Newton, making an angle of 60 degrees to the line of greatest slope. You can see that in the diagram. The coefficient of friction between the particle and the plane is 0.3. Find the greatest and least possible values of T. What does that mean? Greatest and least possible values of T. Now, whenever they ask about greatest and least possible values, when friction is involved, all you have to do is consider the limiting equilibrium cases. That's the general method for such problems. But let me explain it to you. It says greatest and least possible values of T. What does that mean? The system is in equilibrium. In equilibrium means that the opposite forces are supposed to be the same. Okay, the forces acting to the right and left, they're supposed to be equal, and the forces acting upwards and downwards, they're supposed to be equal. So what we have to do is first is resolve the forces. Let's resolve the forces. Let's represent all the forces and resolve them. What are the forces acting? One force is acting downwards, that's weight of the object. 2.5 kilograms is mass. What's the weight? Weight is 25 Newton. There's reaction. Reaction acts perpendicular to the surface like this. There's tension here. And what else? There will be friction. Now, let's resolve tension first, and then we'll think about friction after that. Tension is acting at 6 degrees to the plane. So there are two components that we have for tension. One acting along the plane or parallel to the plane in this direction, and the other acting perpendicular to the plane in this direction. Component adjacent to the angle, that will be T cos 60, and the component on the other side of the angle, that's going to be T sin 60. Okay. Now, these are all the forces. Now, let's resolve weight as well. Weight is going to have one component acting here and the other component acting perpendicular to the plane like this. If this angle is 20 degrees, this angle is also 20. The component acting adjacent to the angle, that's going to have cos. So this is 25 cos 20. And the component on the other side, that's going to be 25 sin 20. And now we need to think about friction. Where is friction going to act? It's not clear because we do not know if T cos 60 is bigger or 25 sin 20 is bigger. Whichever force is bigger, friction will act opposite to that. Now, they are saying find the greatest and least possible values of T for the object, for the particle to remain in equilibrium. What do they mean by greatest and least possible forces? If T was too big, if this force T was very large, what would happen would be T cos 60 would become very large. And if T cos 60 becomes very large, the particle will start moving to the left eventually. And if T becomes very small, If t is very small, if t is very little, because of the weight component, the particle will start moving down the plane. So there is some minimum possible value of t that is going to keep the particle in equilibrium, and there's some maximum possible value of t that is going to keep the object in equilibrium and stop it from moving up the plane, right? How can we find those greatest and least values? We consider two scenarios. One scenario is that the particle is just about to move up the plane. Okay, let me repeat. Since they're saying system is in equilibrium, there are three possibilities. One possibility is that it's normal equilibrium. Okay, one possibility is normal equilibrium. That means the object is stable. Even if tension was to increase by a little, the object will still remain in equilibrium. Okay. Another possibility is that the particle is in limiting equilibrium with the particle just about to slide up the plane. That if tension was even slightly more, it would start moving up the plane. This is one extreme case of equilibrium. And then another extreme case of equilibrium would be that the particle is in limiting equilibrium and it is just about to slide down the plane. So there are three possibilities that we have for this equilibrium. Either the equilibrium is non-limiting, that's in the middle, or it's limiting such that the particle is just about to move up the plane, or it's limiting in the sense that the particle is just about to move down the plane. Since we are looking for the greatest and least possible values of tension, what we do is we consider those two extreme cases so that we have the two extreme values of t, the least value of t and the greatest value of t. We consider these two extreme cases that the particle is either in limiting equilibrium such that it's just about to move up the plane, or that the particle is in limiting equilibrium such that it's just about to move down the plane. We consider these two cases. One of them is going to give us the greatest possible value of t and the other is going to give us the least possible value of t. Now, how do you consider these two cases? Let's consider the first one first of all. Now, what I'm going to do for that is I'm just going to copy this diagram because everything will remain the same. In both of these cases, there's going to be just one difference in both of them. And I'll show you what in a moment. In both of these cases, the difference is when the particle is just about to move up the plane, where is friction going to act? Friction will act down the plane. And in the second case, when the particle is just about to move down the plane, friction is going to act up the plane. These are the two extreme cases that we would consider. And since it's limiting equilibrium, we would say friction is at its maximum value, which is F equals mu r. And now you just have to equate the opposite forces, and that's it. You've resolved the forces already, just equate the opposite forces. Equate R plus R plus T sin 60 to 25 cos 20 and t cos 60 to f plus 25 sine 20 for the first case. For the second case, equate t cos 60 to 25 sine 20. In fact, t cos 60 plus f to 25 sine 20 and t sine 60 plus r to 25 cos 20. And you would get the values of t, the greatest and the least possible values of t from this. Okay. All right. Now let's equate the opposite forces. Equate the forces acting to the left to the forces acting to the right, and equate the forces acting upwards to the forces acting downwards, right? Up, down are considered according to the plane. So this is upward direction, this is downward direction. So if you consider yourself standing on the plane, this is the right side and this is the left side. Okay. Since it's equilibrium, we are equating the opposite forces. Forces acting towards the left, that's t cos 60. On the right, f plus 25 sine of 20. Forces acting upwards, t sine 60 plus r, that equals 25 cos 20. Now from the second equation, we can actually make r the subject, and that gives us 25 cos 20. You can just evaluate that. 25 cos 20, make sure your calculator is in the correct mode. In mechanics, you keep it in degrees. So 25 cos 20, that's giving me 23.492 minus t sine 60. Sine 60 is giving me under root 3 over 2. So that's under root 3 over 2 times t. That's the value of r that I'm getting from this. Now in the first equation, since it's limiting equilibrium, we put f equal to mu r. In place of f, you can input mu r. Cos 60 is 1 over 2. On the left side, we have 1 over 2. That equals mu r plus 25 sine 20. Let me see what that becomes. 25 sine 20. That is 8.5505. You can leave it. You can keep this in exact form as well if you want. That's actually better that you leave it in exact form. Or you can write this in decimals as well. That's your choice. Now mu into r, what does that become? 1 over 2 times t equals mu. We have the value of mu. Mu is given to be 0.3 into r. What's r? R is this whole thing. That's 23.492 minus under root 3 over 2 times t plus 8.5505. What I've done is I've input this thing in place of r here. And now we can solve this and see what this gives us. We'll get a value of t from this. 0.5 t on the left side. On the right side, we've got 0.3 into 23. Now again, that's too many values, too many decimal values. So look out for careless errors. In case there are any, 0.5 t equals 0.3 into 23.492. That's giving me 7.0476 minus 0.3 into under root 3 divided by 2. That's giving me 0.2598 times t plus 8.5505. And that's giving me some value of t, 7.0476 plus 8.5505 divided by 0.5 plus 0.2598. I'm getting 20.53 Newton from this. Can somebody confirm this calculation as well? Is that what you get?
Yes, sir.
Okay, that's the first thing. This is going to be either the least value or the greatest value. In this case, sliding up. Yeah, so it's going to be greatest value. Let's consider the other one as well and see what that turns out to be. Everything is the same as before. The only thing that is changed is the direction of friction. Now, upwards and downwards, when we equate upwards and downward forces, In this case, that's also r plus t sine 60 equals 25 cos 20. So that's the same in this case. That's not changing in the second case because perpendicular to surface, the forces have remained the same. Okay, so we don't have to do this again. We already know that r can be written like this. We already gotten this form from that. Now, in the second case, when we equate the left and the right forces, what do we get from that? We get t cos 60 plus f, that equals 25 sine 20. Now again, t cos 60, what's that? T cos 60 is 1/2 times t plus f. In place of f, you can put mu r, that equals 25 sine 20. We evaluated that here, that was 8.5505. And then 0.5 t. After evaluating mu r, you see we got this in the first case. Nothing is changing, right? We can just input that directly as it is. 0.5 t plus 7.0476 minus 0.2598 t. Right? We've done all of these calculations on the left side already. So we can just use them rather than having to do them all over again. Of course, as long as you've done them correctly and not done any careless error. On the right side, you've got 8.5505. And now you can find the value of t from this as well. Let's see what that turns out to be. 8.5505 minus 7.0476 divided by 0.5 minus 0.2598. And this one is giving me 6.26 Newton. Is that okay? Is this value all right? Okay, good. So this is the greatest value then? This is the greatest possible value of tension. This is going to be the least possible value of tension. This is what we do here. Okay, so in friction cases, in friction problems, when you asked about greatest possible value of a force or least possible value of a force, this is generally something that you always have to do. Consider the limiting equilibrium cases. Consider the limiting equilibrium cases. Okay, on both sides. That the particle is just about to move up or the particle is just about to move down. All right. All right. So we have a block of mass 2 kilograms that's at rest on a horizontal floor. So we have mass 2 kilograms. That means the weight is going to be 20 Newton, right? It's at rest on a horizontal floor. If it's at rest, that means it's in equilibrium, right? The opposite forces are equal. That's why it's at rest. The coefficient of friction between the block and the floor is mu. So we're given the coefficient of friction. A force of magnitude 12 Newton acts on the block at an angle alpha to the horizontal. So we have this force 12 Newton acting here, acting at an angle alpha to the horizontal, where tan alpha is given to be 3/4. When the force acts downwards, as in figure 1, so this is one possibility, the force is acting downwards in this direction, the block remains at rest. So it remains in equilibrium. In the first part, what they ask us to do is, what they ask us to show is that mu is greater than or equal to 6/17. That is what we need to show in the first part, that mu is greater than or equal to 6/17. Now, how do we do this? It's equilibrium, and they want us to show some kind of an inequality. Now, first of all, since it's equilibrium, we know that the opposite forces are going to be equal to each other, right? So let's start with that. Let's represent all the forces that are acting in this case, and then equate the opposite forces, right? Because that is going to still hold its equilibrium, so the opposite forces have to be equal. So let's start with that. Let's represent all the forces acting on this block. First of all, the mass is 2 kilograms. That means the weight is going to be 20 Newton. I'm just going to erase this thing. And we say that the weight is acting downwards. That has a magnitude of 20 Newton. Okay, what else? There's a force of 12 Newton. They have already shown that force here. 12 Newton that's acting on the block at an angle alpha to the horizontal. There's this force acting. What else do we have? Remember the forces that we have to think of ourselves. Weight, normal reaction, friction, tension. Okay, weight we have already represented. Do we have normal reaction? Yes, we have a surface. There is normal reaction. Normal reaction acts perpendicular to the surface, and that is going to act vertically upwards in this case. Let's call that R. Okay, that's not going to be equal to 20 because we also are going to have some component of 12 acting vertically. So we'll also have to consider that when evaluating the value of R. But okay, this is one force that we have, R. That's also represented there. What else? Tension. There's no string here, so there's no tension, right? And then what about friction? Do we have friction? Do they tell us it's a rough floor? They don't tell us it's a rough surface or a rough floor. However, they're talking about coefficient of friction. That means there is going to be friction. Now, in which direction does the friction act? Where does the friction act? Anyone?
Towards the left.
Towards the left side, right? Because this 12 force is acting in a direction such that it would have a horizontal component like this. Friction is going to oppose that, and it's going to resist motion. So friction is going to act in the left direction. So that's the direction of friction that we've got. Okay. So we have all forces represented. Now let's resolve the forces acting on this block. There's only one force that's acting at an angle, that's 12 Newton. We need to resolve that force. Now, I would recommend this. It often saves you from careless errors, that whatever force you have, it's better, it's going to make things easier to understand and less confusing if you represent that force on the side in which it's acting, on the side at which it's acting. So for example, this 12 Newton force, in which direction is this force acting? It's acting in this direction. It's going to make things less confusing if you represent that 12 Newton force here instead, because that's the direction that the force is actually acting in, right? It's acting towards this side, southeast, right? That's the direction of this force. It's southeast in this direction. So instead of having it there, when you are resolving this force, it's going to make things less confusing if you represent it on this side. Because now you can just use your normal method. You say, if this angle is alpha, what about this angle? This is also going to be alpha, vertically opposite angles, right? What's the component of 12 Newton acting to the right side? It's going to be 12 cos alpha, and the component that's acting vertically downwards, and that is going to be 12 sin alpha. Now, it's not necessary to do this to represent this force on this side. It just makes things, in my opinion, less confusing if you represent it on this side, because that's where this is actually applying, right? It's applying in this direction. So we represent this here and we say this angle is alpha. So we have the two components. Now, since it's equilibrium, we just equate the opposite forces. We say horizontally, we have F acting towards the left side, 12 cos alpha acting towards the right side. We have R acting upwards, 20 Newton, and 12 sin alpha acting downwards. Just equate the opposite forces. We say the forces acting towards the left side, they should be equal to the forces acting towards the right side. And the forces acting in the upwards direction, they should be equal to the forces acting in the downward direction. Now, what's the force acting in the leftward direction? Towards left, we have friction. Towards the right, we have 12 cos alpha. So that gives us that friction should equal 12 cos alpha. Okay, what about upward force? Upward force is reaction. So we have R here. Downward forces are 20 plus 12 sine alpha. So we have two equations like this. All right, we've got two equations. Now, what about cos alpha and sine alpha? They have given us tan alpha. Okay, they've given us tan alpha there. What we can do is we can use tan alpha to figure out what sine alpha is going to be and what cos alpha is going to be, right? We've done this before as well. You have tan alpha, you can use a right angle triangle to figure out what the three sides of a right angle triangle are going to be. If tan alpha equals 3/4, how is tan defined? Tan is defined as perpendicular over the base or opposite over adjacent, however you want to write it. Perpendicular over base. Now, if perpendicular is 3, then base would be 4. And what about hypotenuse? Hypotenuse square should equal base squared plus perpendicular squared. And that should give you h equal to square root of 25, which is 5. So if perpendicular was 3 and the base was 4, the hypotenuse of that right angle triangle would turn out to be 5. And using that now, what we can do is we can write down the value of sine alpha and cos alpha, because what is sine? Sine is perpendicular over hypotenuse. Perpendicular is 3, hypotenuse is 5. So we say sine alpha equals 3/5. And then similarly, cos alpha, that's base over hypotenuse, that's 4/5. That will be 4/5, right? So that's cos alpha. You've got the values of sine alpha and cos alpha from here. Now you can just input those values here. Instead of cos alpha, you can now input 4/5 that you got from there. Right? Let's simplify this. Friction turns out to be equal to 48/5. That's the value of friction that we get. Okay, what about reaction? R equals 20 plus 12 sine alpha. What is sine alpha? Sine alpha is 3/5. So we have 12 into 3/5. Let's simplify this and see what we get. So we have 20 plus 36 divided by 5. That's giving me 136/5. Now, I'm not writing this in decimals on purpose, because remember, what they are asking us to do is to prove this inequality, and this inequality does not have any decimals. It has a fraction. So we would want to keep everything in exact form here and not use decimals. So just leave it in this form, in fraction form. We've got the value of friction and we've got the value of reaction. Now, how do we use this to prove that mu is greater than or equal to 6/70? How can we do that? Any idea?
Sir, F is equals to mu r. We can use that.
F is equal to mu r. Why is
Yes.
F equal to mu r? Is this limiting equilibrium? F is equal to mu r when you have limiting equilibrium or when you have object in motion. Are you going to consider limiting equilibrium here? If yes, why? Why do we consider limiting equilibrium?
So
And even if we were to,
we will expect it to be a non-limiting equilibrium.
if it's non-limiting equilibrium, then we have F less than mu r. Is that what we do?
And less than or equal to.
So that means it could either be non-limiting or limiting. We are not
Yes.
sure, right? Yeah. So remember this. When we discussed friction, I told you about this, that we're going to have these three cases: non-limiting equilibrium, limiting equilibrium, or in motion. When we combine the first two cases, we get this thing, that if you have equilibrium, then you can say F is either less than or equal to mu r. And I mentioned it there as well, that it's often used to prove inequalities involving mu. And that's one type of question that I was talking about there. We have to prove an inequality here, and we know it's equilibrium, and we are not sure whether it's limiting equilibrium or non-limiting equilibrium. If it's either of these two things, that means friction is going to be either less than the maximum value or equal to the maximum value. That means it's less than or equal to the maximum value. That means F is less than or equal to mu r. That's what we use here. We say since it's equilibrium and we do not know whether it's limiting equilibrium or non-limiting equilibrium, F should be less than or equal to mu r. That's the condition that we have for equilibrium. When it's not specified if it's limiting or non-limiting. Now we just input those values here. Friction is 48/5. That is less than or equal to mu into R, which is 136/5. Now we can just multiply this on the other side. 5 and 5, in fact, are going to get cancelled. And we're going to be left with 48/136. That's less than or equal to mu. You can simplify this 48/136. What does that give you? That's giving me not the same thing as that. Okay, so maybe there's some error that we have done somewhere. Let me just check. 136/5. I've copied that correctly. Okay, I'm just putting this wrong on my calculator. I'm sorry. 48/136. That's giving me 6/17. Yeah, so that's what we needed. If we cancel this out, this gives us 6/17. So 6/17 is less than or equal to mu. You can just write it the other way around. We can say mu is supposed to be greater than or equal to 6/17. And that is what we wanted to prove there, that mu is greater than or equal to 6/17. Is that okay? That's 5 marks. And you just have to do this. Equate the opposite forces and then use F less than or equal to mu R, because that's what you have in equilibrium. Any problem with this?
No, sir.
No? Those of you who had not attempted this question yet, do you also understand this? Romer, Marino, Tajal? Right? Okay, good. Let's have a look at the second part now. Let's do the second part. Now, the second part says, when the applied force acts upwards as in figure 2, so now this is figure 2. Now the force 12 Newton acts in this direction. In this case, the block slides along the floor. Find another inequality for mu. Okay, now let's consider the second diagram. What are the forces acting in the second case? Again, we've got weight of the block. That's still the same. That's 20 Newton. It's the same block. There's reaction that acts vertically upwards. There is going to be friction. Again, that's also going to be in the left direction because the force is still towards the right side in a sense. So it's trying to make the object move towards the right. Friction is going to oppose that. It's going to act towards the left side. And that's it. These are all the forces. Now we can resolve 12 Newton. There are two components of 12. One component is going to act towards the right side. That's going to be 12 cos alpha, and one component that is going to act in the vertical direction. That's going to be 12 sine alpha. Now we have some horizontal forces again. We've got friction here, and we have on the right side 12 cos alpha. And vertically, we have 12 sine alpha, and we have R, and we also have 20. These are the vertical forces that we have. So we have some horizontal forces and we have some vertical forces. Now, in this case, what they're saying is that the block slides along the floor. What does that mean? It's not equilibrium anymore. The object is moving now. All right, now the object is moving. Now, when the object starts moving, that means these forces are not going to be equal anymore, right? The horizontal forces are no longer going to be equal. The horizontal forces are going to be different. What about the vertical forces? Can we say something about the vertical forces? Are they going to be equal or they're not going to be equal? What do you think? Are the vertical forces going to be the same or different?
Sir, they will be equal.
They're going to be equal. Why? The object is moving.
But it's moving in a straight line.
It's moving in the horizontal direction, right? It's
Yes,
moving in
sir.
the horizontal direction. There's no movement vertically. There's no vertical movement. Since there's no vertical movement, that means the vertical forces are going to be equal to each other, right? So upward force is going to be equal to the downward force still. That is still going to hold. Now let me write that down here. So this is the diagram that we have, the second one. We're saying the upwards force is still going to be equal to the downward force. What does that give us? That gives us r plus 12 sine alpha. R plus 12 sine alpha. That equals the downward force, which is 20. So this should equal 20. That is one equation that we're getting from this. Okay. When we equate the upwards and downward forces, we get r plus 12 sine alpha equals 20. And now it says the block slides along the floor. In which direction is the block going to slide? It's going to slide in the right direction because that's where the force is applying. Now, if it's sliding along the floor towards the right side, what does that mean? The force acting towards the right side, this should be bigger than the force acting towards the left side. Only then the block is going to move, right? So the force acting towards the right side should be greater than the force acting towards the left side. That is when the block can slide towards the right. So in the horizontal direction, we say the force acting towards the right side, it should be greater than the force acting towards the left side, right? Because that is when the block is going to move. Now, what's the force acting towards the right side? Towards the right side, we have 12 cos alpha. That's 12 cos alpha. That's greater than the force acting towards the left side. That was friction. Now, we have this equation and we have this inequality. We have to find another inequality in terms of mu now. Let's see how we can do that. Let's look at the first equation. First of all, what we get from that, r plus 12 sine alpha. What was sine alpha? Sine alpha we found to be 3/5. We can input that here, 3/5, that equals 20. We're going to get a value for r from this. Let's see what that turns out to be. 20 minus 36/5, that's giving me 64/5. Again, keep this in exact form. Don't use decimals, that's better. Leave it in exact form. So I'm getting 64/5 for this. Right? Okay, so that's the value of r. Now, we need an equality in terms of mu. How do we find mu? What we can do here in this inequality is we can say, let's put f equals mu r. Now, why can we do that here? Because remember, we talked about this in friction. When the object is in motion, in that case as well, friction is equal to its maximum value. Friction is equal to mu r. So now in this case, the block is sliding along the floor. Sorry, it's sliding along the floor. So the friction is going to be equal to mu r in this case. So what we can do is we can replace friction with mu r on the right side. What about cos alpha? We figured this out above. It was 4/5. And now we can just input all values. 12 into 4, that is 48/5. That is greater than mu into r. What's the value of r? R is 64/5 from there. Now, just make mu the subject, as in take mu to one side, everything else to the other side. You can take this to the other side. 5 and 5 are going to get cancelled. 64 goes to the denominator there. And you have 48/64. That is greater than mu. If you were to simplify this, that is going to give you 3/4. So 3/4 is greater than mu. That means mu is less than 3/4. That's another inequality that you're getting in this case. Okay. Now, since the block was sliding along the floor, what we said was the vertical forces are still going to be equal because there's no movement in the vertical direction. And remember this is always going to be the case in your syllabus, because in your syllabus, you only have linear motion, one direction motion. You cannot have 2D motion. So there's not going to be projectile. In this case, they specifically mentioned this in the question, that the block is sliding along the floor. But you can just remember this in general as well. You would never have objects moving in projectile motion like this in M1, because that's not part of your syllabus. So The objects are only going to slide along the surface. Okay, if they're moving along the surface, they're going to slide along the surface. That means you can always equate the forces acting perpendicular to the surface. These forces are always going to be equal. Now, since the block was sliding along the surface towards the right side, we said 12 cos alpha should be greater than f, and that helped us find this other inequality in terms of mu that we were looking for. Mu is less than 3/4.